In this video, we're going to talk about integer representations and algorithms. In particular, we're diving into the concept of numbers written in different base forms. So for us, we use base 10. So for example, when I look at the number 965, I am thinking of this in terms of tens. So this could be thought of as 9 in the hundreds place, or 9 times 10 squared. 6 in the tens place, or 6 times 10, and 5 in the ones place, or 6 times 10 to the 0. So each number can be thought of as being multiplied by a power of 10. That's why our numeric system is base 10. But if you're going to go into computer science, you need to know some other base formatting. For instance, base 2 binary code is big, same with octal and hexadecimal. Those are often used for computing and communications. And then just a quick note, we know that the Mayans and the Babylonians use different base number systems as well. Mayans were base 20, Babylonians were base 60. Just a little history there. So the idea is you can write numbers in this form, like how I wrote the 965 up here, in their base form when you know what the base is and you're using powers of that base to write the number. So let's just kind of look at some examples. So if this integer here is at base 2, we're interested in how that's, what that is in our base 10 number system. So to figure that out, we need to write it in its own base system. So here's how we would do that. The first one here, I'm gonna have to kind of keep track. That one right here, that is, let's see, let me count them off here. 1, 2, 3, 4, 5, 6, 7. And so it's the 8th. Okay. Let me make sure I did that right. Sorry. Actually, I missed one. Okay, so it's the ninth number, but the very first number, the very first one is base is 2 to the 0. So actually, maybe I'll work backwards just to kind of prove that point. Wow, let me erase. There we go. So this number here is 1 times 2 to the 0. And then the next is 1 times 2 to the 1, and so forth. Okay, so the last number is going to be 2 to the 8th, even though there are technically 9 digits here. It's actually grouped by 4s. I don't know why I didn't see that. Okay, that's fine. So plus, okay, now 0 to the 2 times 7th. Obviously, that's not very useful to us. It's going to 0 out. 1 times 2 to the 6th. 0 times 2 to the 5th. 1 times 2 to the 4th, and then the rest, 2 cubed and 2 squared, are both 1s. Okay, I made it fit relatively well. I'm happy. Okay, so you literally need to multiply this out. Like you literally are going to figure out, what 2 to the 8th is. So grab your calculator and let's do this. So 2 to the 8th, that comes out to 256. This is 0. 2 to the 6th. I feel like I should know these, but I don't remember them for some reason, is 64. 2 to the 4th, I know that one, that's 16. 8, 4, 2, and then the last one is 1, right? So real quick, just so we're clear, these two were zeros, so I didn't even count them, okay? Everything else I did the calculation for, and then of course 2 to 0 is 1 times 1 is 1. All right, great. Adding those together, you should get 351. And that is this number, 351 in binary code, base 2. I'm sorry, I shouldn't say code, in binary. So it's base 2. Let's just try that again. In fact, if you want to pause the video and give this one a try, and then you can see me work through it, that's fine. I'm going to figure out what the last number is. So 0, 1, 2, 3, 4. So 2 to the 4th. So 1 times 2 to the 4th, 1 times 2 cubed, 0 times 2 squared, 1 times 2 to the 1, and 1 times 2 to the 0. And let's see, that's going to be 16 plus 8 plus 2 plus 1. So 27. I can actually calculate that one without the calculator. Yay. There you go. So exciting. So base 8 is another one. That's when base 8 is using the digits 0 through 7 to represent numbers. Okay. So if this is base 8, this particular number here, let's figure out what it is in our base 10 notation. So just a quick comment, you'll notice just like with binary, right? All of the numbers for binary are ones and zeros, right? And those ones and zeros are placed in different place values for base 10. These numbers are zeros up through 7. So the largest number we'll possibly see is 7 as a digit. Okay. Okay. So let's see. Let's count off. This is 0, 1, 2, 3. So this is going to be 7 times 8 cubed, 0 times 8 squared, 1 times 8 to the 1, plus 6 times 8 to the 0. So that's how it's written out. And it's octal expansion. Okay. And if I do the calculation here, oh, here, let me go ahead and go below and actually calculate. So I don't have this. Let me go ahead and plug it into my calculator. 8 cubed is 512 times 7, which comes out to 3,584. This is 0, so I'm not going to bother. Plus 8 plus 6. So I'll just add 14 to this on my calculator and I get 3,598. So that's the base 10 number system, or we call decimal, the decimal system that we're used to. What is the decimal expansion of this in base 8? So it looks like it could be binary, but they include this little indicator, right, to let us know that it's base 8. So even though it's all ones, it is in fact base 8. Okay, so that's 0, 1, 2. So that's going to be 1 times 8 squared plus 1 times 8 to the 1 plus 1 times 8 to the 0. So 64 plus 8 plus 1 comes out to 73. All right. And then last, hexadecimal expansion needs 16 digits. So we only have 10. Therefore, they add letters to represent the other part of the numerical system past 9. So A, B, C, D, E, F are actually letter representations in the hexadecimal expansion. I'm sorry, number representations in the hexadecimal expansion. And therefore, we have to kind of think of them as numbers, all right? Because you can't have a 2-digit number representing it. Now, just so we're kind of clear, all right? And they say it, A through F represents the decimal numbers 10 through 15. So A happens to actually represent 10. We just can't put 10 down because 10 looks like a 1 and then a 0. B represents 11. C represents 12 and so forth. Okay. So the idea is, I just have to finish writing it down because I'm feeling a little anal retentive about it. Okay, there we go. So that's the idea. They represent numbers, but we use the letters because needing a single digit to actually be part of the hexadecimal system. Okay, so here, let's see that in action. So we have this one that actually has some letters in there. It's base 16. So let's figure out what it is in decimal form, or base 10. So that's 0, 1, 2, 3, 4. Okay, so the first one is 16 to the 4th power plus, okay, now I see A, but A is really 10 to the 3rd power, 16 to the 3rd power plus, okay, E, that's 14 to the 2nd power, 0 times 16 to the 1, and then B is 11 times 16 to the 0. Okay, so grab your calculator. Let's do some calculating here. Whew, big number. Okay, here, I'm going to go ahead and actually calculate what 2 times 16 to the 4th is, and I get 131,072 plus. All right, so this is 40,960 plus 14 times 16 squared is 3,506, sorry, 84. E4. Then we have a 0 and then 11. Okay, so let me just add those up. 4,000. Oh. And 131,072. Okay, putting it all into my calculator. I am getting 175,627. Oops. Wait, I did not get that. Oh, wait. No, I did get that. Okay, good. Sorry. I have the correct answer and I copied the correct answer, but then I checked my calculator and it wasn't matching. But they did. I just forgot to add the 11 at the end. Cool. All right. So there you go. Let's try it one more time. A little simpler this time, not so complicated. E and 5. Okay, so E is 14. And since this is 0 and 1, it would be 14 and 16 to the 1 plus 5 times 16 to the 0. So 14 times 16 comes out to 224. Plus 5 is 229. All right, so there we go. We have the base number systems kind of hopefully understood how they work. Now, if we want to convert between the base number systems, in particular between each other. In other words, if I don't want to convert to base 10 and then convert it back, right? Like, or, we want to be able to have a way of converting between the number systems. So it is a division process to do this, okay? You divide by the base that you're trying to convert to, all right? And you will often have a remainder. This remainder becomes the first digit to the right on the expansion, okay, on the resulting number. And then you keep dividing. It actually helps to see it by example, but I went ahead and put in the steps and then the algorithm as well for it. But let's actually work through an example. I think it helps to kind of see it written out. So I want to convert this to base 8. And it's currently base 10. So I want to convert it to base 8. So here's how I do that. I take my number to 1, 2, 3, 4, 5. And I'm going to divide it by 8. Okay, so grab your calculator, do 1, 2, 3, 4, 5 divided by 8, and you're going to get a decimal. I got 1,543.125. Okay, so that means that 8 goes into this number 1,543 times. So if I do 8 times 1,543, that gives me 12,344. So here, I'm just going to write this below, but I'm going to erase this in just a second. So this is 12,344. And if I subtract that number from the number I'm working with, that is a remainder of 1. So this is the number in base 8. So I literally grabbed my calculator. Oops. Wow. I meant to do it in red. Sorry, there we go. Grabbed my calculator and divided this number. I'm going to do it in green. And I got 1443.125. So then I figured out what 8 times 1543 is. I don't know why I used that symbol. There we go. And I got 12,344. And then I subtracted this number and got the remainder of 1. I didn't really need to do that subtraction, but there you go. So this became this part right here, and this became the one there. All right, so hopefully you see how that worked. I'm not going to show that work again. We'll just go ahead and work it out through the calculator. I might talk you through it, but I'm not going to go ahead and do that. But here's what I am going to do. Let me go ahead and erase the highlight. All right. I'm going to take this result here, that 1543, that's the quotient, and I'm going to divide it again by 8. So grabbing my calculator, putting 1543 divided by 8, I get 192.875. So this is 8 times 192. Okay, so let me figure out what 8 times 192 is. 15,036, and I'm going to go ahead and subtract that from 1543 and get my remainder of 7. So there we go. And I'm just going to keep doing this. Okay, I'm going to keep doing this until I can't do it anymore. So I'm going to take now the 192 and divide it by 8. Divided by 8. Now my calculator, I got 24 exactly. So that means it doesn't have a remainder. 8 times 24. Doesn't have a remainder. So remainder is 0. And then I'm going to go ahead and divide 24 by 8, which I happen to know, again, doesn't have a remainder. It's 0. And then I'm going to take 3 and divide it by 8, but of course I can't. So this is 8 times 0 plus 3. Okay, so we've divided by 8 repeatedly. And now here is the actual answer in base 8. These are the numbers that make up the answer in base 8, and it's done in reverse order. So 1, 7, 0, 0, 3. So that is the answer, the representation in base 8. So you do put it in reverse order in terms of how we produced the numbers. All right, let's try another one. So we'll do a binary expansion this time, 241. So I'm going to take 241 and I'm going to be repeatedly dividing by 2. So 241 divided by 2. That's 120.5. So that's 2 times 120, which means there's a remainder of 1. All of these remainders, by the way, are going to be either 1 or 0, right? Because it's binary. So our answer is going to come out to 1s and 0s. So that makes this one a little bit easier. Okay, and then I'm going to take 120 now and divide it by 2, which is going to be 60 plus 0. And then 60 divided by 2 is 30 plus 0. 30 divided by 2 is 15 plus 0. And then 15 divided by 2 is going to be 7 with a remainder of 1. And then 7 divided by 2 is going to come out to 3 with a remainder of 1. 3 divided by 2 is going to come out to 1 with a remainder of 1. And unfortunately, I'm like running out of space here. I try to squeeze the last one in. So 1 divided by 2 can't happen. So it's 2 times 0 plus 1. All right, there we go. There are the digits of the answer. So I want to go in reverse order. So the first number is the last number in my answer. So 1, 3 zeros, and then 4 ones. 1, 2, 3, 4. And there it is, the base 2 notation of this number. All right. So you just repeatedly divide. Just divide over and over and over again. And the remainders are what's making the decimal representation. Okay, so here's what's kind of nice. The book has this little table which shows us some of the number conversions. And this makes it easier to convert between the other number systems, binary, hexadecimal, and octal, without converting first into our system, decimal. Okay. So for instance, this is a number in base 2. Let's say I'd like to have it in octal or hexadecimal, but I don't want to do binary first. I'm sorry, decimal first. I want to just switch between them. I can use this table to help me do that. Okay. Here's how we do it. For octal, when you look at the octal for binary, so octal is going to go from 7 right down. So looking at the largest number for octal, it's 3 in binary. It's no more than, it's 3 digits. The minute it moves to 8, it goes into 4 digits. And that means then that 4 digits is a good expression for hexadecimal. Okay. So here's what I'm saying then. If I want to easily find this in octal, so let's start with octal. I want to think of this number in pairs of 3s. Okay. So currently it's kind of done by 4s, which means it's kind of set up for hexadecimal, but we're going to regroup it so it's by 3s. Okay. So here's how that's going to look. I'm going to start with the last number over here, and I'm going to take that 100 and that's going to be the number I'm going to be converting. So I'm basically going to break this up into threes. So those three numbers, there's the 100. The next three numbers is 111. The next three numbers is 010. The next three numbers is 111. And then the next three numbers is 11, but because I'm going to try to think of it as three numbers, I'll put 011. Why not? Okay, so this is it written out for helping me convert to octal. Okay, so here's what we got. I'm going to use the table above to help do this conversion. So for instance, this first number, 01111, is right here on the binary system. And in octal, that represents the number 3. So that's 3. 111. Let me erase those. 111 is right here. And so for octal, that's the number 7. 10 is next. I don't know if I can erase the highlight. There we go. The number 10 is next. So 10 is right here. So that's 2. 111 again, that's 7. And then 100, that's 4. Oops. Okay, so this is the octal expansion then. 3, 7, 2, 7, 4, base 8. That's how we'd write it in base 8. Cool. All right, let's do hexadecimal. So by 4s for hexadecimal. And in fact, the number is actually set up by 4s already. So I'm just going to put for the first number 2 zeros in front of the 11. And then 1110, 1011, and 1100. Okay, so this is the number going by 4s. Okay, so 11 again is here, but then we're looking at the hexadecimal this time, and it still happens to be the number 3. Oops, computer was not up to date when I wrote it. There we go. All right, then we're going to go to 1110. So that is right there. Ooh, there it is. Okay, so in hexadecimal, that's E. Then we'll do 1011. That's this number right here. Hexadecimal, that's a B. And then last 1100, right next to it, is a C. So there we go. In hexadecimal form, this number is 3EBC, base 16. There we are. So that table's kind of nice to use to convert between them. If I want you to do this conversion, I'll give you that table to work with on an exam. All right. Otherwise, it'd be allowed to use. So I'm not going to make you memorize them. This is the answer. You don't have to memorize the table. Okay, let's look at algorithms on these other base number systems. What's kind of cool is it's actually possible to add and multiply in the other number systems, and it's not too complicated. You just kind of have to understand that when you're working with certain decimal systems, you can't exceed certain number values. Okay, let me give you an example. I feel like this works so much better by example. So let's say I want to add these two numbers in their base 2. All right, so if I want to add these base 2, I'm going to actually set it up as like a standard addition. Now, the book does this a little bit differently. I feel like what I'm going to show you is a little bit easier. If you want to see how the book does it, you can go ahead and check it out. They kind of write it a little differently based on not needing to write it in this vertical form. But I find it easier to do it in this vertical form and kind of do old-fashioned addition. All right, and I'll kind of explain it as we go. So here we go. The first two numbers, 0 and 1, they add up to 1. Fabulous. The second two numbers, 1 and 1, add up to 2, and that's a problem. Binary doesn't have 2s, right? So 2 becomes like a 10 almost would be. So like here, sorry, I should probably just do a quick example in our number system. Base 10. Okay, here. All right, there we go. So in base 10 number system, we do 7 plus 6, that's 13, but I can't fit 13, right? So I have to carry the 10 to the next column, and then that adds up to 12. And I'm okay with that because the last number happens to bump up into the next place value. All right, so when it's too big, you carry it into the next column. All right, that's what happens here. If you hit a 2 in binary, a 2 in binary means you bump up to the next column. It becomes a 10. In fact, if you look at our table, all right, in our number system, 2 is a 10. So coming back down here, when those two add up to 2, that's really a 10 in binary, so I carry the 1. And then again, 1 plus 1 is 2, so I have another 10. All right, so I carry the 1. Okay, now this time I have a 3. All right, so 3 is like the equivalent of 11. And the reason is, I'm trying to verbalize how I'm thinking of this. I'm sorry, I'm struggling a tiny bit. The idea is that 3 divided by 2 comes out to 1 with a remainder of 1. There we go. That's where the 1, 1 is. All right. 2, when divided by 2, comes out to 1 with a remainder of 0. So that's where the 10 is coming from in base 2. So 1, 1, base 2, 10, base 2. So I'm just dividing the numbers by 2 and figuring out what their remainder is. Okay. You won't really see anything bigger than 3 because you'll never carry anything more than 1. And the most you'll be adding up is going to be the ones. All right, sorry, I didn't mean to erase the number. I just was trying to, I don't even know what I was trying to do. Let's just go back and make it give me the numbers back. Come on. I don't know why it's mad at me, but it is. It's so mad at me for asking it to backtrack. I apologize. I upset the computer. You should never upset the computer. So here's what we do. We'll just rewrite the number. 1, 1, 1, 0. Okay, and when we added, we carried a 1 here and a 1 here. All right, there we go. Let's try multiplication. It's going to be pretty similar. Okay, we're going to kind of use the same logic. Actually, you know what? Let me do another example base with addition, and I'm going to just do it right here next to it. So I just want to make sure that we're clear. I feel like I stumbled a little bit over that. So let me just give you a second example. I'm going to make it up. So let's do 1, 0, 1, 0, base 2. And we're going to add to it 1, 1, 1, base 2. Okay, so let's add these two numbers up. Oops. So 1, 0, 1, 0, and 1, 1, 1. Okay, so every time we add 0 and 1, no problem. I get a 1, not an issue. When I add 1s together and get 2, that's a problem. It becomes 10 because 2 divided by 2 is 1 with a remainder of 0. All right, again, we carry the 1 here. Oops. And I'm getting 2 again, so those two add together and give me 10. Carry the 1, I get 2 again, 10, but this time I don't have to carry the 1, I'm at the end. So there we go. This is the answer, by the way, base 2. Base 2. All right. Okay, hopefully that felt a little smoother. Let's try multiplication. That should say multiply. Multiply. All right, so we're going to multiply 110 times 101. So remember, let's do an example of multiplication, old school. All right, let's do 110 times 36. All right, so remember, here's how it goes. We first start with 6 times 110. So 6 times 0 is 0, 6 times 1 is 6, and 6 times 1 again is 6. Then we add a place value of 0, and we multiply 3 now times 110. So 3 times 0 is 3. I'm sorry, is 0. 3 times 0 is 0. 3 times 1 is 3. 3 times 1 is 3 again. And then we add these together and get 0, 6, 9, 3. And of course, we might have to carry. Okay, so kind of remember that process. That's the process we're going to do. So we're going to start with the 1 here on the far left. So this is the 1 we're going to start with first. So we're going to multiply 1 times each of those numbers. Okay, so the multiplication is going to work exactly as we anticipate. So it's going to still be 1 times 0 is 0. 1 times 1 is 1, and 1 times 1 is 1. Great. There's the first number. Now I'm going to add a 0 and multiply the next number, which happens to be 0. So 0 times each of those numbers is 0, 0, 0. Great. Now I'm going to go to the next number, which is 1. And to do that, I'm going to first add 2 zeros down here. And now I'm going to multiply. 1 times 0 is 0. 1 times 1 is 1. And then 1 times 1 again is 1. Okay, so I'm going to add these together. And remember, anytime we hit a 2 or a 3, we have to think of it first converting to binary. Okay, so first column is 0. Second column is 1. Third column is 1 again. Oh, that's so nice. We didn't have to do anything weird. So there we go. There's our answer, base 2. All right, not too bad. Okay, that's it. Okay, that's right. I thought I decided not to do division. It wasn't, they didn't even have any examples of division, so I didn't bother. And the last little part of the section had this thing about modular exponentation. And again, I didn't really see too many examples I wanted to have us do on that. So this is actually the last topic we kind of cover in this section, and that's it.